All right, today, we're putting on our detective hats and going on the hunt for some of the trickiest criminals in the microscopic world, spirochete bacteria. See, these guys are absolute masters of disguise, causing diseases that can look like dozens of other things. So our focus today? It's all about the clever detective work it takes to finally unmask them.
And that really is the central mystery, isn't it? When your main suspect is a tiny spiral-shaped bacterium that loves to hide deep inside the body, how do you even prove it's there? You can't just, go in and look for it. You have to be a lot smarter than that.
Well, just like in any great detective story, the answer is to follow the trail of evidence. You follow the clues it leaves behind. It's this whole fascinating process of elimination, confirmation, and sometimes seeing right through a clever deception. So let's meet our prime suspects.
Okay, so our main culprits are a class of bacteria called spirochetes. A classic example is Treponema pallidum, the little guy that causes syphilis. What makes them so tricky is that they are notoriously hard to grow in a lab or even see directly. And that forces doctors and scientists to get creative and rely on indirect methods to hunt them down.
So our medical detectives basically have two main strategies. First, they can look for indirect clues, signs of damage the culprit left at the crime scene. Or they can look for direct clues, something that is specific to the culprit itself, kind of like a fingerprint. In the lab world, we call these non-treponemal and treponemal tests.
The investigation almost always kicks off by casting a really wide net. These first tests, these screening tests, are designed to be super sensitive. That means they are excellent at picking up any possible sign of an infection. The goal here is pretty simple. Don't let a single clue slip by.
And what's really fascinating is what these tests are actually looking for. They don't detect the bacteria at all. Nope. Instead, they detect antibodies our own bodies make when our cells get damaged. Specifically, they're targeting something called cardiolipin, which is a lipid that gets released from our damaged cells. It's literally like finding a broken window after a break-in.
But as any detective knows, when you cast a wide net, you always risk catching more than just your target. This high sensitivity, well, it comes with a trade-off. What happens if that broken window wasn't actually caused by your suspect?
And this slide right here shows the problem perfectly. A whole bunch of other things can cause similar cell damage and trigger our bodies to make these same antibodies. We're talking stuff like mono, hepatitis, chickenpox, even being pregnant can cause a false positive. And this is exactly why an initial positive result is just a lead. It's not a conviction. So, this brings us to the absolute golden rule of this investigation. Any clue you get from that wide net screening test must be confirmed with a much more specific method. You found a clue. That's great. Now you have to prove it actually belongs to your suspect.
Okay, so this is where our detectives bring out the big guns, the high-tech tools. Phase 2 of the investigation is all about confirmation. It's about using tests that are incredibly specific and can definitively link the evidence back to our culprit.
Right, so unlike that first round of tests, these treponemal tests are looking for the bacterial equivalent of a fingerprint. They detect antibodies that our body has made specifically against the Treponema pallidum bacterium itself. This is a direct link, which is what makes these tests so incredibly specific. And these tests can get pretty sophisticated. Take the classic FTA-ABS test. It actually uses this special substance, a sorbent, that's made from harmless spirochetes to first soak up any antibodies that might cross-react. This makes sure that when the test finally does light up, it's only because of antibodies to the real syphilis culprit and not one of its harmless cousins. Pretty clever. But hey, even with the best tools in the world, a good mystery always has a twist, right? Sometimes the evidence itself can be totally misleading. So let's look at a few ways the clues can deceive even the sharpest medical detective out there. This is probably one of the weirdest, most counterintuitive twists in all of diagnostics. Imagine this. You run a screening test on a patient who clearly has all the symptoms. You are sure it's going to be positive, and the result comes back negative. How on earth is that possible? It's called the prozone phenomenon. It turns out that in some tests, having too many antibodies in the patient's blood can actually gum up the works and overwhelm the test, preventing it from working properly. It's like a room that's so crowded nobody can actually shake hands. That's kind of what's happening on a microscopic level. It causes a false negative. Luckily, there's a really elegant solution to this. When a sharp lab tech sees a negative result that just looks off, maybe a little rough or grainy, they get suspicious. And the protocol is super simple. Just dilute the patient's sample with saline. By watering it down, you reduce the concentration of antibodies, and suddenly the test can work correctly, revealing the strong positive result that was hiding there the whole time. Now, these principles, screening, confirming, troubleshooting, they aren't just for syphilis. They apply to a whole family of spirochete-related cases, and each one presents its own unique set of challenges for our medical detectives.
Let's take Lyme disease. Here, the problem is often the complete opposite of the prozone phenomenon. In the first few weeks of a Lyme infection, a patient might have that classic bullseye rash and all the symptoms, but their body just hasn't had time to produce enough antibodies to show up on a test. This leads to a ton of false negatives early in the disease.
So how do you solve that one? Well, you bypass the antibody evidence completely. For early-stage Lyme disease, the most specific test you can run is a PCR test. It doesn't look for the body's response at all. It looks for the culprit's genetic fingerprint, the bacterial DNA itself. You can't get much more direct evidence than that.
This table kind of pulls it all together and summarizes the different strategies. For syphilis, the big challenge is wading through false positives and keeping an eye out for prozone. For Lyme, it's all about overcoming those early false negatives. And for another spirochete disease, leptospirosis, the challenge is all about timing. You've got to get that blood sample in the first week. Each case really does require its own tailored approach.
Now check out this quote, because it reveals another crucial piece of the puzzle. Those fingerprint tests, the treponema ones, they tend to stay positive for life, even after you've been successfully treated, so they tell you if a person has ever been infected. But those damage tests, the non-treponema ones, their levels drop as the patient gets better. This makes them super useful for monitoring if a treatment is actually working.
So if you take one thing away from all this, let it be this. Diagnosing these diseases is never about a single yes or no result. It's about a process, an algorithm. It's about understanding the story that's being told by a logical sequence of tests, where each one answers a different question in the investigation.
And all of this leaves us with one final big question. This entire complex stance of screening and confirming and troubleshooting, it all exists because these culprits are just so hard to catch directly. So as our technology gets better and better, what does a future look like where we can just bypass all the indirect clues and get a rapid, definitive answer right from the start? That right there is the next frontier for our medical detectives.